What happens when numbers get so large that they break calculators? Today, we're asking a question that looks simple, but hides a mind-bending truth about extreme mathematics. Which is larger, m to the power of n factorial, or the factorial of m raised to the n? You might have an intuition, but I guarantee, it's probably wrong for most cases. Because the answer isn't always the same. It depends on a hidden relationship between m and n. Take a look at this phase diagram, our map of impossible numbers. This map tells us exactly who wins the battle of the gigantic exponents. The red zone? That's where m to the power of n factorial dominates. The blue zone? That's where the factorial of m raised to the n reigns supreme. And that black line? That's the equivalence boundary, where the victor flips. This table shows where two massive expressions cross over, depending on the base m. The theory predicts the crossover happens around n almost equals em, about 2.718 times m. Look at the numbers. For m equals 2, the target is 5.4, actual crossover is 5. For m equals 5, target 13.6, actual 14. By m equals 10, target 27.2, actual 28. Across all bases, the real crossover is always the nearest integer to e times m. Different bases, same constant, e, controls the phase transition. Then, let's compare digit counts in two explosive expressions. On the left, we have m to the power of n factorial. On the right, the factorial of m raised to the power of n. For the base m equals 2, when n is small, the factorial of 2 to the power of n has more digits. But around n equals 4, the ordering flips, 2 to the power of n factorial suddenly becomes larger, and then it completely dominates. Now look at base 3. The same pattern appears, but the crossover shifts later, around n equals 8. Different bases, different crossover points. The factorial growth of a product can beat the power of a power, the power tower, and the switch happens at the predictable threshold, n equals em. Let's test our map with some real giants. First up, m equals 2, n equals 100. So we're comparing the factorial of 2 raised to the 100 versus 2 to the power of 100 factorial. Now, 2 to the power of 100 is already a massive number, it's about 1.26 followed by 30 zeros. So the factorial of 2 raised to the power of 100, is the factorial of a number with 31 digits. That's a lot of digits. How many exactly? About 3.76 times 10 to the power of 31 digits. But what about 2 to the power of 100 factorial? Here, the exponent itself is factorial, which is a mind-boggling 9.33 times 10 to the power of 157. So we're talking about 2 raised to that unimaginable power. The winner? 2 to the power of factorial 100 by an absolute landslide. It has approximately 2.81 times 10 to the power of 157 digits. This is so much larger, it's not even comparable. And if we look at our phase diagram, with m equals 2 and n equals 100, we're deep in the red zone. Let's try another. M equals 3, n equals 99. So we compare 3 raised to the power of 99 factorial, and the factorial of 3 raised to the power of 99. 3 to the power of 99 is a huge number, about 1.7 times 10 to the power of 47. So the factorial of 3 to the power of 99 has around 8.05 times 10 to the power of 48 digits. And 3 to the power of 99 factorial? With 99 factorial being about 9.33 times 10 to the power of 155, this number has approximately 4.45 times 10 to the power of 155 digits. Again, 3 to the power of 99 factorial is the overwhelming victor. And our phase diagram? For m equals 3 and n equals 99, we're squarely in the red zone. So, it seems m to the power of n factorial always wins, right? That having the factorial in the exponent is the ultimate power? Well, here's where your intuition gets absolutely shattered. Let's try m equals 99 and n equals 99. We're comparing 99 to the power of 99 factorial versus the factorial of 99 to the power of 99. Okay, 99 to the power of 99 is a number with about 198 digits. So the factorial of 99 to the power of 99 is the factorial of a 198-digit number. That's a lot. How many digits? Roughly 7.28 times 10 to the power of 199 digits. An almost unimaginably large number. Now, 99 factorial is also huge, about 9.33 times 10 to the power of 155. So 99 to the power of 99 factorial has approximately 1.86 times 10 to the power of 156. And the winner? It's the factorial of 99 to the power of 99. It has more digits than 99 to the power of 99 factorial. This time, the factorial of the base wins. And if we look at our phase diagram, with m equals 99 and n equals 99, we are firmly in the blue zone. So, why the flip? How can changing m and n so drastically change the winner? The secret lies in the underlying growth rates of these functions. These numbers are so massive, we can't even count their digits directly. We have to use logarithms, and a special mathematical tool called Stirling's approximation. Let's break it down. To compare m to the power of n factorial, and the factorial of m to the power of n, we take the logarithm of both. This allows us to compare their exponents more easily. After applying logarithms, the core comparison becomes, is n factorial greater than or less than n times m to the power of n? It turns out that, n times m to the power of n, is usually much larger than n factorial for lower values of n, relative to m. This is why the factorial of the base, the factorial of m to the power of n, wins for small n or large m. But factorial growth is incredibly powerful. As n gets very large, n factorial will eventually overtake any simple exponential like m to the power of n. And the exact point where it takes over is revealed by approximating n factorial using Stirling's approximation. To compare them, we switch to natural logarithms. Using Stirling's formula, the natural log of n factorial behaves like n times natural log of n minus n. So natural log of n factorial is approximately equal to n times natural log of n minus n. While the natural of n times m to the n is equal to n times the natural log of m plus the natural log of n. Now we're comparing growth rates directly, and this setup will help us reveal where the crossover happens in next step. When we solve for the point of equilibrium using these approximations, a beautiful and fundamental constant of mathematics emerges, Euler's number, E. The crossover point occurs when the ratio of n to m is approximately equal to E, or about 2.718. So, that black line on our phase diagram? That's the equivalence boundary, and it perfectly traces the equation n equals E times m. If your values of n and m fall below this line, meaning n over m is less than the constant E, then the factorial of m to the power of n is larger. If they fall above it, meaning n over m is greater than E, then m to the power of n factorial is larger. This isn't just a fun fact about big numbers, it's a testament to the elegant, often surprising, consistency of mathematics. Even with numbers too vast to comprehend, simple constants like E dictate their ultimate behavior. So, what's your biggest takeaway from this journey into the realm of gargantuan exponents? Did this surprise you? Let me know in the comments below. If you enjoyed unraveling the mysteries of these impossible numbers, hit that like button, subscribe for more mind-bending math, and click the bell icon so you don't miss our next adventure. Alright, it's time to wrap up. Leave a comment below, and don't forget to like, share, and subscribe for more fun math problems. See you next time, and thank you for watching.